Good evening, everyone. Welcome to today's problem solving section, week 7, Force Applied Accelerated Experiment. So, the performance of a processor is measured using flops. Flops means floating point operation per second. So, the performance of a processor is measured using flops, and flops is floating point operations per second. So it is in terms of for the AI based on whether it is training or whether it is inferencing or training itself, like we can have 16-bit flops or we can have 32-bit flops or a hybrid. So we see the amount of parameters used by the Microsoft ResNet model was 60 million parameters, and that is like to be trained. In order to train them, the amount of computation spent is about 7 e- exaflops. And when we move to the 2016, series of miniature, 2016, the computation problem to a different set of problem in the space of natural language processing NLP. So, which has around 300 million parameters, resulting into the almost the amount of performance which are required to train the model is in the range of 20 exaflops. And in the 2070, Google Neural Machine Translation uh, almost the parameter reach a few billions, like almost like now the parameter count is billion parameters that needs to be trained. And so we look at the amount of parameters that need to be trained for realizing the realistic or real world examples. We like have uh, increase in the parameter which is needed for training a neural network. So the motivation for the multi GPU programming is like we see starting from the 2017. Um, there is like a first paper from the first one. The paper is from the Google training a set of image classification in neural network on a 300 million image data set, and the result using a recurrent neural network. So the initial result suggests the relationship between the data size and the accuracy is linear in an algorithmic space. So here, like the relationship of the dataset size means like dataset size increasing at the same level, the accuracy also kept on increasing. So with the increase in the data, we are seeing like say for the large models or character large language model, image classification, attention speech models. Uh, the increase in the data set size, there is an logarithmic relation, linear relationship to also increase in the accuracy level. So there the need for distributed deep learning. So, so it is estimated that we are currently seeing here is another representation of the, like, where the x-axis is at the logarithmic scale, and the training data set size. Y-axis is the generalization error at the logarithmic scale. So on the extreme left, uh, small data region, and we see the error is not getting better, but it reduces, it increase in the dataset size. But also some, you can see certain level that the error becomes irreducible as well. So the estimation that, like, we are currently in the power law region, and we can notice how the generalization error reduces with the increase in the training dataset. The increase in the dataset size also comes with the increase in the compute power required for convergence, and that is what is shown in the next few slides. So the scaling law, in this paper, which was published, the scaling laws for neural language models. So there is a linear relationship on the compute requirement with increase in the model parameters and size of the dataset. So in the first set of slides, we like saw the amount of flops which are required when there was increase in the data sets, and also the size of, or the number of parameters which were supposed to be trained. So this gap between the compute requirements for larger networks can be solved by utilizing multi-GPU and distributing our deep learning workload. So this allows us to, like, further parallelize, giving us faster convergence. So the critical things which is like, um, so now the like the critical things which is like, we do not talk about anymore about using for a large problem statement a single GPU anymore. So this motivation for the multi GPU training. So now, like, we can predict how much data we will need to meet a performance goal. So there are different relationship of papers which kind of define the amount of data that is required. And because of the nature of this relationship for a lot of problems, the data volume can be very, very high. So we are talking about the relationship and the amount of time which it will also take. So the benefits of using the multi GPU. So if we are, like, using particular time duration uh, for some work that, like, wanted to be submit, and like we could do multiple things, like train on more data, and say I have a fixed duration, I want to do this training in say 2 days. But now I, like, I can provide it with more data within the 2 days. uh, I can do more iteration on it to see if the convergence if it is converging. Or I can do, in fact, like rather than a small model, I can try train on a larger model. So we are like trying to get better results on the same results faster, or the same results faster. So there are two ways. One is like we want to solve the same problem faster, and the other one is like we want to save the time, and this is like a kind of permutation and combination, or we want a better results by trying out something which is larger, like trying out on more data, more amount of augmentation to the data, and trying on larger like models. So the this what the perspective is of using multiple GPUs. So this is comparison going from one GPU to multi GPU. On a CPU, it will be like multifold folds slower. So if we are training a ResNet 50 for 90 epochs on ImageNet dataset, ImageNet dataset for ResNet on A100 is our largest generation architecture. It's from the NVIDIA called as Ampere. Ampere is one of the largest, latest generation architecture. It takes around 14 hours to train on the overall dataset. And if we combine and take, say, with the DGX machine, which has 8 A100 and 100, so it is taking like 3 hours. So the time reduces from 14 hours to 3 hours. And if like one of the pre-trained model BERT for a set of 8 V100, it takes around 153 hours to train. And so all of these trained data set are kind of like retrained and provided to us. And ideally, we're like supposed to work on the additional data set and do the transfer learning. But coming from back to the topic of our multi-GPU, if we are training from scratch for this data set, if we want like 18 to 16, the time reduces. But we see that at the level of scale that we can run it on about like bird like model, which is very much scalable in nature. So it is designed to be scalable model, and we can see it runs on 1024 V100s, and it gets completed in 1 hour. And now if we like were to work in this space of large national large language processing machines translation, and if we like are working on real life data set on larger models, so the time taken on a single V100 or 8 V100, if we access a cluster with say 1024 V100 cards, will be so we can reduce the time it takes to get results by using more number of GPUs. So the two main methods of in the training workload across the GPU is like spread the input data across the GPU, and it is known as data parallelism. And the second one is the model computation across the GPU. So here it is called model parallelism, and this is like there are like various ways to implement different layers on different GPU or single like shared layer onto multiple GPU. So for example, if we have say batches of images and say we have millions of images or say 10,000 of images, and we are spreading this input data across the GPU so that this like in the multi GPU training is called as data parallelism, because we are doing it in distributed like by distributing the batch of the data across the different GPUs, and this is most common or straightforward way to increase the training throughput, because if we see it is like parallel, means every image is kind of independent of each other and we are distributing it across different GPU. So like there are methods of multi GPU screening. The first method is referred to as data parallelism, where we are like basically distributing the batch of images, like generally say say a batch of image to we will give to every GPU, and they can spread out like it's more straightforward way and parallelly to just distribute the images. The second approach is the model computation across the GPU, also referred to as model parallelism, and this is like more complicated way, and there are various and different methods to implement this. For example, if we put different layers of a neural network onto different GPUs, or sometimes we may also share the single layer onto multiple GPUs. So it is much more complicated way to make it work. And so we can see that the data parallelism is the very most straightforward way of using the multiple GPU, multi-GPU training. So we have two types of parallel approaches used in the deep learning, the data parallelism and the model parallelism. Uh, Data parallelism could run on the same net, could like put it on the same network in different workers or the GPUs. When I say like worker, we are referring to different GPUs, but with the different input data for each worker, and then the outputs are aggregated. While the mode of parallelism is used when the network is big enough to fit in the single GPU memory, like when we are saying newer set of network which have few billion parameters, and if we see like mm, GPU memory is a kind of limited in nature, the latest GPUs will give around 80 GB of CPU memory. So if the network is that large, which does not even fit into a single GPU memory, the model parallelism is one which is necessary. A combination of this can be used, and they could be referred to as hybrid parallelism. Same if we want to train a huge um, network in a multi-node setup. We can expand the network across two nodes containing two or more GPUs, and then each node can then process a different input and aggregate that. And this can be use both model parallelism as well as data parallelism. types of parallelism. So the data parallel part. So here, like each and every worker is using one GPU. So particularly, like we can assume that basically like 4 worker, and in this 4 worker, all are using 4 different GPUs. And in this way, the network or the DL network, we can see the same network is replicated across 4 GPUs. So in this same network, which gets copied to all we have some network which gets a copy to neural network, which gets the copy to all this 4 GPU nodes. So the same network is replicated across different GPUs. So in this way, the same network to different GPUs. So the data parallelism, the data set is divided into n parts, which is say like n number of GPUs. So here we need 4 copy of the model and 4 chunks of data and the corresponding data chunks. And the gradients are calculated. So the we have the like process of forward pass and then the backward propagation. So after the forward pass, we get the loss, and then we will calculate the gradient with respect to the loss function. So they are calculated for each copy of the model. So we can see every worker is basically going to create that gradient, and then all the models basically exchange the gradients, which is subsequently averaged. So all the models will independently like basically work, and they are going to calculate their own gradients, and then also then after the forward propagation after a particular level, like at each which iteration and all, then each and every worker exchange their gradients across with each other, like each and every other worker, and finally they do the averaging. So if we see in the data parallelism, we are increasing the speed, like speeding up the training by distributing the data. All the workers are training on different data set. All the workers also get the same copy of the model. All of these things are very important. The gradients, which are the weights changes, are exchanged during the training. And if you are done into the like the max of the deep learning, we see that certain amount of like two terms why the convergence will differ when we run on a single node versus multiple nodes, or when we run on single GPU versus multiple GPU. So when we started every model, like first of all giving different data set, every model here have could have been initialized to different ways. So we could be in different landscape of the loss function, and that like starting at different location, and then finally the idea here is that when we start doing this averaging, we may not reach the same destination within the set of iteration within the loss landscape to reach the global minimum. So here itself, like we can start like what is the difference when we are starting distributing the work. So like there is some randomness which is brought in the deep learning framework itself. Model parallelism. So this is the model parallelism. So here the model, like we have worker 1 is actually like working on a particular layer inside the neural network, while the worker 2 is working on another layer and 3 on the another. So we are creating a graph, and each and every worker on the GPU is working on different layer, while all of them are using the same data. So in the model parallelism, one model is divided into n parts, where n is equal to the number of GPUs in. So say here we have 4 GPUs, and each of the part of the model is placed in a separate GPU. The model is placed on like separate GPU or separated out by say, then the batch is sequentially calculated on GPU 0, 1 and GPU n. So this is where the forward propagation completes. Then the backward propagation is done in the reverse order, starting from the GPU n and ending with GPU 0. So the forward propagation, the way it will work is goes from 0 to 1, 2 and 3, and in the it goes to the n in the forward propagation, while in the backward it is done in the reverse order, starting from GPU n to GPU 0 and 1, like 1 and 0. So the advantage of this particular approach is that we can train a model in the way that is done, not fit in one GPU. So example like networks are becoming larger, so not fitting right now in the 80 GPU space of one GPU. So this is also a drawback if we see if model parallelism were computing on GPU number 1, and whatever certain number is in progress, all the rest are ideal. As we can see, GPU 0 in the forward pass works, then GPU 1, 2, then it goes to N. And in the backward 4, 3, 2, and it goes to the it goes in the backward. So this problem can be solved by switching to asynchronous GPU operations. So what we are saying is that seen till now is like synchronous operation, where like one will wait till the time the other is over, and this is what is called synchronous operation. While we can also use something called as asynchronous operation. So there are the parameters that we are going to decide and use it in different frameworks. Like we are going to use data parallelism and are going to use the model parallelism. How many workers we are going to run it on, are we going to use synchronous or use asynchronous? All these decisions which are made by the developer of the network. So it's like kind of summarization of the communication part of it, which is like comparison of the methods. And as we can see, there are here the GPU 1 and 2 are using the data parallelism, and as it's like we can see, passing it as a different data, like new different data, but the same set of layers exist in both the GPUs. And at the every level, like what we are trying to do actually is averaging the gradients. So we are like basically communicating the gradients across and then finally averaging them. On the right hand, we can see the model itself, where we will have like exchanging slightly different things. So we are exchanging the activation, and we are like basically the communication is of different type. So we are not basically like averaging, but we are actually exchanging the activation, and the communication pattern is slightly different, or actually it is much more different. The reason is to understand this will be explained in the later slides. So we were referring to some terms like asynchronous and synchronous communication. So we will be focusing on the data parallelism approach. So within this, we have two, synchronous and asynchronous. This is the synchronous approach, and the approach where all the workers are kept in synchronous, which means every worker is in sync, which means they know the status and the value of the other worker. And in the every step to be made sure that they apply individual updates to the model, and all of them at any point of the time have the same copy of the model. This is like very important aspect of synchronous communication. While in the asynchronous data parallel approach, the workers basically obtain the variables from a parameter server. So we can see there is one more component which has got added, which is called the server. As the name suggests, we might like the server is basically responsible for talking and giving an update to all the different clients. So who are the clients here? The clients are the workers or the GPU themselves. And the GPU, the workers obtain the variables from the parameter server and store the results back after processing. The parameter server could apply those updates and update the variables. So this is also the allows the workers to work independently. Now it is very, very critical. Like if we see on the left side, especially in the synchronous communication approach, since every worker need to be in sync with the other worker, they are always going to go into step-by-step manner. So even if one worker is lagging behind, it will affect the scalability of all the other workers because they have to wait till the end time, all the workers at the same state. So in the case of the load imbalance, or if one worker is lower as compared to the other, we may get to the scaling issues. While in the case of the asynchronous communication with the parameter server, the workers actually work independently of each other. And we are going to see in the next slide that we are going to focus on the synchronous data parallel approach. But asynchronous has its own way and it kind of finds its own space to make the scaling better. So whether we are using either synchronous or asynchronous, or using the data or the model, and how to split and that everything, like we will discuss, and what is the kind of like common across all the communication of them. So the worker needs to communicate either with each other or with the parameter server, or at what level they are going to do averaging with each other, each and every worker. So like we are like, are they going to do activation, sync activation communication? So whatever is the approach that we are going to follow, it is like going to be dependent on the machine and how GPUs are connected to each other and how the machines are connected to each other, because the communication is going to be defined if we want to scale it out. So the what matters is the system topology. In the networking is in the system is in this computer architecture world, the definition of is called as system topology. So topology within a node, how like how these GPUs are connected to each other across the node and how are these two nodes connected to each other and like how the GPUs connected to interconnect. All this is like basically going to define the performance of the scaling of the model. And this we will see. So particular example if we take. So here we are having something called as NV switch. So this is a baseline version and this is the version which of a particular server which is referred to as NVIDIA DGX2. And what we are seeing here is the system configuration. In the first one, the baseline consists of server, which is of type DGX1, and DGX1 is another server. So DGX1 has 8 GPUs. So we have like basically 8 GPUs, and what we are doing is the baseline version is basically that we have two GPU nodes, which is two GPUs connected to each other via the interconnect like InfiniBand interconnects. So in this case, the InfiniBand type is also given. What is like having a node which has 16 GPUs. So instead of going across nodes, we are like within the node, and within the node we are using specialized switch, which is the NV switch. And when we do not go across and within the node, like we can see here that like amount of performance gain that we get over the baseline version is much higher. So the baseline version is We get 2.x speed up by using a network topology of a machine, which can do fast communication with low latency. And we are going to like see about this bit. So when we get a larger amount of differences between a machine which we are running on it, so the throughput and latency. Um, Say if the gradients are actually like very small, so we do not need a network which is having very large high bandwidth, but we might require a network which is having very low latency. So one concept, so the latency is the time taken for the transfer of a single packet of data, which means if I were to just send, uh, say like if I just were to go from here to the airport alone, that's the like transferring single packet of data. Understanding the system topology, latency versus throughput. So latency is the time taken for the transfer of a single packet of data. So based on the kind of the bus or whatever like method, we can like reach faster or slower. So so when we have any network, when we are testing and doing a speed test, we get two numbers. Latency could be given in terms of how many millisecond or microsecond it is takes to do ping. So it is the ping latency. So the latency of the data being sent from one place to another. The throughput is basically measuring the amount of data that is being transferred in one unit of time. Like I transfer 10 of them together in one shot, and I can transfer 1 KB of data or say 1 MB of data, much more amount of data. So how much can I transfer in one shot? So there are two different things that are kind like related to each other, and they are basically related by the equation throughput is bus bandwidth divided by the latency. So interconnect is the way the two systems are connected. So the two systems are connected to each other via one or other form of interconnect. The say for example, two system may be connected via LAN, which is the model normal Ethernet or via say PCI Express bus. So if they are within the same node or two GPUs can be connected within the same node using some other interconnect called say PCIe. For example, it's like the latest generation architecture like A100. A100 is the specialized interconnect. Has the specialized interconnect which is called NVLink. If we see the Ampere card which is present the later generation, they have a particular interconnect called NVLink. And this is third generation NVLink, and we can see here that each and every, so we can get up to like 50 giga bit per second per signal pair. So we have different number of signals and we get up to 50 gigabit per signal pair, and we get like 12 of them. So if you divide it by 2, because we can do it both in and out parallel. So basically we have 12 links which can run at in and out speed of 25 gigabits bytes per second. A total amount of which is to like 600 gigabytes per second of total, which is twice more than a previous generation which was V100. So basically the type of the GPU we are going to use, the communication across and the NVLink bandwidth are something we are like using if we are using the pre-sensor or the Google Cloud or the other instance. So does it even have an NVLink? And when we start using multi GPU, we might get into the scaling. We may not get the scaling that we expect because it does not have a specialized network protocol which is there in E100 called as NVLink. So based on the type of system topology that we have, we may or may not have these kind of features. Like here we can talk the feature of GPU direct. The GPU direct basically means it is like one GPU is connected to the other GPU in a friendly peer-to-peer manner, or which can allow GPU direct. The GPU can directly talk to each other, which means that one GPU can directly transfer the data to the other GPU. It does not need to depend on any other thing to do the transfer. That can, and that is like the independent, completely independent on the kind of system that we are having GPU in. The method, the other method is also the communication concept, which like the communication interconnect. So here also we have multiple types of interconnect. So this is like a host staging. The data which is being transferred from different GPU, the data is transferring from GPU 0, and you can like we can see here is the traversing via the PCIe bus to the CPU first, and then from the CPU it is triggered in the buffer stage buffer before we copied into GPU 1. So based on the type of the system topology or the method that we have, we are going to basically like have these things. So whereas if we have in the second method, if the GPU direct can establish, and if we are getting a better system topology in the peer-to-peer communication approach, they can directly be connected via interconnect. So here we can see the interconnect is in this PCIe switch, and the GPU 0 is directly talking to the other GPU via the PCIe switch. Or it can use the switch, the NVLink protocol, and it just talk to. So this is that like much more higher bandwidth and lower latency as compared to PCIe switch. So because some of the numbers which we are like seeing here is based on the kind of the hardware that we see, based on the network topology or the system that we have, we will get different performance numbers. So So when we install this NVIDIA drivers, we can use this particular command here. Like it has some NVIDIA SMI Topo -M. This NVIDIA like here the topology minus the -M stands for matrix format. So here the particular output of the system, which is say digits 1, showing the GPU 0 to GPU 7, and then we have like the infi band adapters of the and then from GPU 0 it has a like we can also use NV1 NVLink 1 um, so a network topology which do not have really like a good interconnect pattern, they may result into not so much uh, of good performance number when we are trying to scale across. So we can use this command NVIDIA -SMI topo -M to see the network topology. So here we can see two CPUs. Both the CPU have a PCIe switch. Via the PCIe switch, the GPU and the CPU are connected to each other via the PCIe bus. And within the GPU, we have like 8 GPUs, and those GPUs are connected via the NVLink. So we can see here that once the NVLink protocol, well, this one uh, is the PCIe buses. So we are trying like to do the communication. Suppose like we are a system where we have this PCIe bus and we do not have NVLink. So the first thing is like going to the we are like going to do this is that we are going to load the data from the file system to the GPU to the CPU to the GPU. So like we are basically doing the data loading over the PCIe bus. So we load the file to the CPU to the PCIe and then to the GPU. So now when we are running it in a parallel, and we are also using at the same time gradient averaging, and that we will be doing it using the PCIe. So we are going to use the same PCIe for reading the data and transferring the data to the GPU. And also like we are using it for the gradient averaging part, which is like result in choking the PCI bus alone. The data loading and the gradient averaging are basically sharing the same communication resources, leading to congestion. So when if we have a different system and the system basically had NVLink inside it, in the particular case like we can basically do this, that the data loading actually happens while the PCIe bus from the PCPU taking this particular part, while the gradient averaging can basically happen via the NVLink. So the GPU can talk to each other via the NVLink rather than via the PCI, the same PCI Express bus which is being used for the data transfer as well. So there is no sharing of communication happening across the resources and hence resulting into almost no congestion and resulting into much more better scaling. Uh, we could say that the performance part of it. So the point of view of the frameworks like PyTorch or TensorFlow, all of them they basically take care of all this communication behind the scenes for us, and what may or may not get good performance. The NVIDIA has provided libraries which can result into better performance. It tries to find a lot of things like all of your framework, like PyTorch, TensorFlow, and all. They can use library when we activate multi-GPU computation. A library called as NVIDIA Collective Communication Library or NCCL. The NCCL is a library which provides many things. Like it provides the fast multi-GPU and multi-node communication. It provides the fast communication routines uh, for multi-GPU, multi-node acceleration. NCCL improves the application performance by maximizing inter-GPU bandwidth utilization. And also it is very easy to integrate or optimize for high bandwidth kind of networks. And it is basically integrated into all of the major deep learning frameworks like Caffe, Microsoft Cognitive Toolkits, MXNet, and PyTorch TensorFlow and all. So we can see here is that it enables multi-GPU NVLink or PCIe based. It enables multi-node, InfiniBand based topology. It also does automatic topology detection. NCCL provides a lot of things like it does the scenes behind. Like the first thing that it does is the topology detection. What is the looks at the overall system? It builds a graph including where all our GPU, NIC card, InfiniBand cards, CPU could I be traversing the PCS switch or does it have NVLink or does it have NVSwitch? So it does the topology injection for different settings. It does a graph extensive search to find the optimal set of rings or trees. So it tries to find out what is the best traversal path. It does a graph traversal and tries to find the best path whenever we want to communicate across. And it does the graph connection based on the right. And finally, then uh, return that. And then finally, it will run all of this. The communication happens not via the CPU, but it actually runs inside the GPU as small GPU kernels and the CPU threads are basically for network communication. So it uses a small amount of GPU for basically doing this kind of things. So we can see it like there's a lot of things behind the scene for us that we do not have to worry about. The only thing is, if you want to have a system which has better system topology, it will help you doing it. So when we are using the NCSEL separately, not within this framework, it basically does something like this. Like we will write a code like first is to create a unique ID or the communicator. We are going to create communicator and then we, we are like going to do it a different communication in form of like NCCL send or receive, or we we can do the collective communication like all radio broadcast, which are particularly very well known in the MPI world. But the good thing is basically all of these frameworks behind the scene whenever we want to do this gradient averaging across and when we want to communicate. All this code has been written behind the scenes so that we can do like do not have to worry about this. But the library NCCL is the general presented and we want can utilize it if needed. So the frameworks like TensorFlow, Horowitz, MXNet, PyTorch, all of them are very important to know that how this framework basically implement this, and each of them have different topology, basically way of using multi-GPU, and they call it as strategy. Like a PyTorch, we will have torch load distributed. It has three main components. While in Horowitz is a very popular distributed framework that works with the TensorFlow and PyTorch or MXNet, it is completely different framework. And we had shown like in the previously uh, NGC as a something like NVIDIA HTTP Cloud. All these containers support multi-GPU and the right version for NCCA, and all are contained into one particular unit. If we want to do it manually, it is very error prone. So rather than that, we can actually use the NGC and make sure that we have all the dependencies which are set. So with that, we go for distributed deep learning. So till now we have seen two concepts, latency and throughput. Latency is nothing but the time taken for the transfer of a single packet and how of data. How much time does it take for me to like reach from one destination to the other? The second one is the throughput, is the quantity of the data that can be transferred in one unit of time. Like you can transfer 1 KB or 2 KB, and it is important from point of view of scaling. The scaling law kind of like define, and that could be independent of the system on which we are going to run the multi GPU or any kind of distributed deep learning job. And also the particular system architecture, say called NVIDIA DGX, consists of say two CPUs. So this we have seen two GPUs can directly communicate. NVIDIA's library types of kernel. The TensorFlow has like its own way of distributing the work. The TensorFlow uses an API called as Distribute API, and this Distribute API can choose different things and they are different strategies. Like we can choose synchronous communication, asynchronous communication, and you can also choose the platform. It can run on multiple types of distribution, like pure CPU mode across to what can do it in Google TPU also, or you can do it on GPU. So the TensorFlow has its own way of distributing the work. The TensorFlow uses an API called as distribute API, and in this distribute API we can choose different things and their different strategies. Like we can choose synchronous communication, asynchronous communication. So I think since it's right. So we to define the strategies for say TensorFlow version. So in the TensorFlow, if we choose mirror strategy for distributing the work, it will basically indicate that we are going to use synchronous distributed training on multiple GPUs, but on a single machine, which means we are going to run on or distribute the work across multiple GPU, but within the same machine, it will do like go across different nodes. So it actually creates one replica per GPU. So we can see here is what kind of doing data parallelism, and each variable in the model is mirrored right, and they are kept in sync because this is a asynchronous programming environment. Multi-worker mirror strategy is the way very similar to mirror strategy, but we have multiple workers, each potentially having multiple GPUs. So it is most similar to mirror strategy, but it only works within the same node. But we are going to have more number of worker targeting multiple GPUs. We also have a central storage, which again does synchronize training. The parameter server strategy. Parameter server is like a common data flow method to scale up the model training. So it is like basically working on the concept of synchronized programming program where a parameter server, the training cluster, it consists of multiple workers and parameter servers. The variables are actually kept on the parameter server and they are read and updated by each and every worker. So each and every worker does need to talk to each other. They just talk to the parameter server as well as like we can Also define other kind of strategies like one device strategy also. So when we are using TensorFlow mirrored strategy, in that particular case, we can have tf.distribute.mirror strategy.scope. So that we are trying to say tf.distribute dot mirror strategy, and we can create the model. Whenever we are creating a model, the model creation happens within the scope of that strategy. So we can see here we are saying with the strategy of scope, and inside that we are defining the model. So the model is defined inside the scope of the strategy that we have defined. So this is how the work of the TensorFlow works. So all of the frameworks support distributed deep learning. This is one particular referring to TensorFlow APIs. So if we look at this from a point of view of this support, basically it has multiple implementation, and this implementation are based on two types of or two axes. One is synchronous versus asynchronous. And the second one is based on the hardware type that we are going to run this particular strategy on. So in the synchronous versus asynchronous, we have touched this the previous lecture, in the synchronous training, all the workers train over different slices in the synchronous fashion, and the gradient aggregation happens at every step. While in the asynchronous, all the workers work independently, training on the input data and updating the variables asynchronously. The second axis is the hardware platform. TensorFlow supports multiple hardware. It supports GPU. It supports multiple distributed training across CPU and also cloud TPUs, which is Tensor Processing Unit by Google. So TensorFlow supports total of 5 strategies that we have used on the GPU. There are more strategies. Ones that can be like used for accelerator more like GPU, Google TPU, and all. But we are like going to see in this section the usefulness of the accelerators. First is the mirror strategy. First it is like synchronous in nature. It creates the replica of the GPU. So one of the key thing is that part of its parallel data parallel, and we can see it will create a replica for GPU, and each variable in the model is mirrored, and the variables are always kept in the sync. That is what mirror strategy works on. Multi-worker mirror strategy. The keyword there is the multi-worker, similar to mirrored strategy, but it creates multiple workers, each with potentially multiple GPUs. It creates similarly to mirrored strategy copies of all the variables in the model as each device across all the workers. There is another strategy which can be used, which is strategy central storage strategy, where variables are not mirrored. The updation of the variables or the main copy is kept in the CPU, uh, and the operation are replicated across local GPU. So all like if suppose there are only one GPU, in that case like it resides only on a particular one GPU. Parameter like data parallel method to scale up. It helps because all the workers are not talking to each other while they fundamentally talk to parameter server, and it consists of multiple workers. So the variables are created on the parameter server, and they can read and update by the workers in each and every step. Another is one device strategy, where we can define where to place all the variables on particular single device. Um, this is another framework which is forward, and then is a library for distributed learning. It was initially a tool for internal use at Uber, which was later open source for the community. Apart from the features which we have, it also has additional tools like such as Horoword timeline, which can be used to analyze the time taken for each operation and optimize them. So we can see what all features it has. It supports backend. It like supports TensorFlow. It supports Keras, PyTorch. So we can think of Forward as a meta framework over existing framework like TensorFlow, PyTorch, and all. So it is very easy to install. There is almost minimal code changes that we have to do, and moreover has been used for multiple exercises and for even doing exascale kind of computing. It uses some advanced techniques to do really good scaling, or it has different types of optimizers which are used in those scale scenarios. So Horoward has been used widely and is proven to be scalable across. This is from a paper extra scale deep learning for climate analysis, and the model was trained on the Summit supercomputer. With that, let us move to the scaling training using the Harvard. So the key point again is that petaflop simulation and the number of GPUs across which it has run. So we can see it is scaling pretty well. So here in the Harvard, let's like something we have MPI. MPI stands for Message Passing Interface. It is one of the most prevalent distributed computing model in the high performance computing environment. And like for who are working in the molecular dynamics, computational fluid dynamics, and all those kind of high performance computing domain, if we want to scale or if we want to distribute our work across multiple nodes, the model which is used is message passing interface. And Horowitz uses the MPI model, which where each multi CPU thread could be launched and each of them corresponds to one GPU, which is very different from the TensorFlow case where one CPU thread are used to handle all the GPUs. So this is the design choice by the Harvard team. And it's very, very critical to understand this because this is one of the fundamental reasons why Harvard can scale actually really well. The steps which are required in the code to make use of Harvard is like MPI, we need to do initialization. Initialization is key to finding out different aspects where behind the scene and forward kind of sets to context them there. Then you can pin each CPU to a single process. So we could define multiple runtime. At runtime, we define how many processors we want, and then for each process, we will pin a particular GPU. So we can pin one or more GPUs in a single processor, like TensorFlow. Again, we are going to wrap the optimizer or also inside the Horowitz distributed optimizer. So we are going to wrap the existing optimizer, which will be responsible for calculating or delegating the gradient computation to the to the original optimizer. So it does the gradient calculation to original optimizer, whichever is there, but it also takes the responsibility of averaging the gradients across multiple processes using MPI features like all reduced, all gathered, which are very known in the MPI community. And it is proven to be working really well with different kind of topologies using InfiniBand like structures and all. And then applying those average gradients, and once it is done, so it's basically broadcast the initial variable states across rank 0 to all the other processes. And if we want the code, we will have to change certain code of the safety checkpoints and other things only by the workers again. So we do not have want all the workers or all the process to save their checkpoints because the same state is maintained by everyone. So there is no need for everyone writing to the same checkpoints, pointing values and corrupting them in short. So from the code point of view, um, we first import and then we initialize the hello world for the entire script. We then are going to pin the GPU to a single process and we can see here the code, which is first of all getting all the listed devices available. We get the particular list and for every GPU we basically based on the rank of the particular process, like the process which we are like launching. However, if we are launching two processors, there will be process one which get a rank 0 process. One will get a rank of process two, will get a rank of 1. So basically on the rank which every forever process gets, we could do set visible device, which means every process will get its own GPU. In the TensorFlow, the strategy API could handle updates reading the weight and making ideal updates. Moreover, we can use the optimizer of the distributed optimizer method. Updates are critical and are kept in sync. So if we see here, we can choose our own optimizer and then wrap the optimizer inside the distributed optimizer. So the current optimizer will continue to work, but the distributed optimizer, as we said before, responsibility there for it to make sure that it will basically take over and do the all reviews and all the other part of it. And then we do the averaging of the gradients and then we can also define the callbacks from the rank 0 to all the process. So we said we can save checkpoints and we could ideally like only one worker and worker 0. So that they to present the other workers from corrupting them. So prevent the other workers from corrupting them. So we can say only if the rank 0, then only we are going to save the checkpoint basically using a code. This is the flow of the forward part. So next, previous year assignment questions. Which of the following statement is true about the model parallelism? So if we see option 1, it says uh, easy to implement. So the model parameter, like model parallelism is generally harder to implement than the data parallelism because the model is split across devices, carefully requiring careful partitioning and communication. So this is false. Second, all workers train on different data. So this is describes data parallelism where each worker process different data copies of the model. In the model parallelism, the model is split, not the data. So this is also false. In the model parallelism, gradients are exchanged between each of the model on the device during propagation. So the communication of gradient does happen. So this is true for the data parallelism. In the model parallelism, since the model is split in across devices, the activation from part of the model must be passed to the next. So this is the key characteristics of the model parallelism. So what is model parallelism? Model parallelism. So the answer is activations are passed between the GPU. So model parallelism is a technique used to train very large neural network model that do not fit into the memory of the single GPU or device. Instead of replicating the whole model on each device like data parallelism, the model itself is split into different parts and each part is placed on different device. Say we split the model, GPU1 holds layer 1 to layer 4, GPU2 is for layer 5 to 6. Then forward pass. When the input data is it started at the GPU first GPU, then pass through the levels it holds. The output activation from the GPU1 then are then sent over the communication bus to GPU2, which continues the forward pass, say using the NVLink or the PCIe. Backward pass during back propagation, gradient flow in the reverse order. The second GPU calculates the gradient for its layer and sends the data to the of its input activation back to the first GPU. So, and which uses them to update their own parameters. Because activations and gradients must be passed between GPU, communication and speed bandwidth are critical bottlenecks, but it is used when for big models which does not fit into one GPU memory. Which TensorFlow distribute API strategy is suitable for synchronous training across multiple devices where variables are not mirrored but placed on the CPU with the operation replicated across all the local CPU. So if you see synchronous training across multiple devices, variables are not mirrored across GPUs. Variables are placed on the CPU. Operations are replicated across all the local GPU. Okay. So if you see the strategy, mirrored strategy, variables are mirrored, copied across all the GPU. So each device has its own copy of variable and the gradients are synced during the training. So this is not what we want because variables are mirrored. But question says variables should not be mirrored, so this option is wrong. Designed for this next is parameter server strategy. So this is designed for distributed training with the parameter server. Variables live on the parameter server. Workers do computation. Good for large scale distributed training over multiple machines. Variables are not mirrored but stored centrally. But it's mainly for multi-machine setup rather than the local GPU. So this is also not true. Central storage strategy. Variables are placed on a single device, actually CPU. Operations are replicated on all GPU. Variables are not mirrored but centrally stored. So this is the correct answer. And one device strategy, all computation and variables are live on a single device and not suitable for multi-GPU. So the correct answer is central storage strategy. This strategy places variable on central device like CPU, replicates operation across multiple GPU, and does not mirror the variables. Third question. Which command displays the GPU direct communication matrix of the system? This strategy places variable on the central device. Let's see. If I hope this question is clear. The next question, third question. The correct command to display the GPU direct communication matrix, the topology showing the connectivity and communication path between GPU and node is first one A. So displays the topology matrix showing how GPU, CPU, and other devices are connected, including GPU direct communication path. And my -P shows the PCIe paths, but not the matrix layout. And -I or -C are not valid options for the NVIDIA -SMI topo. Next question, which TensorFlow distribute API strategy involves worker reading and updating variables stored on parameter server during training steps? Parameter server. Yes, it is the correct answer. So why? So the question is like the strategy where worker read and update variable stored on parameter server during training is parameter server strategy. Why? Because parameter server strategy is designed for distributed training where variables live like spread on parameter server like are stored in the parameter server centralized storage nodes. Workers or training devices pull variables from this server, compute gradients, and update the variables on the server. So this setup is often used for large-scale training across multiple machines. Next, mirror strategy. Variables are mirrored across devices, updated synchronously. Central storage strategy. Variables are placed on single device, usually CPU, with operations replicated on GPU. One device strategy every runs on a single device. So the next question. NVIDIA library provides topology-aware multi-GPU collected communication primitive. So which is NVIDIA's library? This NCCL. So the NVIDIA library that provides topology-aware multi-GPU collective communication primitive is NCCL, which is NVIDIA collective communication communications library. So NCCL is designed for high performance communication between GPUs, optimized for NVIDIA GPU topologies. Supports collective operations like all reduce, broadcast, reduce, and all gather. Topology aware means it optimizes communication paths based on how GPUs are connected, PCIe, NVLink, etc. So the trust, it is a C++, this is a C++ template library for parallel algorithm like STL for GPU and CU BLAS, BLAS, NVIDIA's GPU accelerator for the linear algebra. Next is NVML. This is NVIDIA's management library for monitoring and managing GPUs. So the answer is NCC. Next question. Which TensorFlow distribute API strategy places all variables and computation on a single specified device? One device, yes. The correct answer is one device strategy. So the TensorFlow strategy that places all variables and computation on a single specified device is one device strategy. So the one device strategy runs everything on a single device, whether it's a GPU or a CPU. So it's useful for testing like when we want like to explicitly specify one device for all computation and variables. So the other strategies, mirrored strategy, variables are mirrored across uh, multiple devices. Parameter server strategy, variables are live on the parameter servers and computations on the worker. Central storage strategy, variables placed on one device like CPU, computation replicated on multiple devices. So the correct answer is one device strategy. Next question. Which of the following statement accurately describes forward? C. Yes. Minimal code changes are required to integrate forward with existing framework. We will go one by one. However, supports only TensorFlow for distributed computing. It is false because it supports multiple frameworks including TensorFlow, PyTorch, and MXNet. Next, for facilitate easy installation for usage. Yes, this is also true because it is designed to be easy to install via PIP or Conda install and integrate smoothly with the existing code bases. Next is multiple code changes are required. Minimal code changes are required to integrate moreover in existing framework. This is also true as one of the moreover strength is that we can typically only need to add a few lines of code to enable distributed training. And Corolla is limited to scaling up to small number of GPUs. This is false because it's designed to scale efficiently to large number of GPUs and nodes. So the two options are correct. Corolla facilitate easy installation and usage, and minimal code changes are required to integrate Corolla with existing framework. Next, state whether the following statement is true or false. So, in the horror mode, checkpoints are saved only on worker 0 to prevent corruption by other workers. Is this statement true or false? Yes, it is true. Because in horror mode, typically one worker 0 is responsible for saving checkpoints to avoid conflicts or corruption that could occur if multiple workers try to write to the same checkpoint file simultaneously. Next is which TensorFlow distributed API strategy is designed for synchronous distributed training across multiple GPUs on one machine where each GPU has a replica of all the variables. Mirror. Um, yes. Correct answer is mirror strategy. Because the mirror strategy replicates the entire model on each GPU, variables are mirrored, copied across all GPUs. Synchronization synchronizes updates during training. ideal for multi-GPU single machine setup. So other options, parameter server strategy, designed for distributed training across multiple machines. Variables are like on the parameter server and workers compute gradients, usually used for asynchronous or larger distributed setup, not specially optimized for single machine. Multi-GPU synchronization training. Variables are not mirrored across GPU but stored up centrally on the server. Then central storage strategy places all variables on a single device. Operations are replica across GPU, but not variables are not copied to each GPU. So this means GPU must communicate with the central variable storage during training, which can cause bottleneck. So it's not ideal if you want GPU to have full replica of the model. One device runs all computation and variables on a single specified device. No distribution or replica happens across multiple GPUs, so it cannot leverage multi-GPU simultaneously. So mirror strategy is the answer. It is fully replicates a full model on each GPU and synchronizes updates. The next question is scaling efficiency can be defined as. Option B. Actually, the correct answer is option A. Uh, Scaling efficiency is equal to total samples processed for unit time divided by this. All we can also bring it down by denominator. Number of APU samples processed for unit time per unit. Because what is scaling efficiency? When we are training a model using multiple GPU, we want to see how well the training speed scales as per, like, as we add GPU, more GPUs. So ideally, if we have one GPU processing 100 samples per second, then two GPU should process 200 samples per second. Four GPU should process 400 samples per second. That's perfect linear scaling. Scaling efficiency measure how close we get to this ideal. So scaling efficiency is total number of process uh, per unit time by number of GPUs into samples processed per unit time per GPU. Total sample process per unit time is how many samples all GPUs together are processing each second. Number of GPUs, how many GPUs we are using. And sample process per unit time per GPU is how many samples a single GPU can process in 1 second, measured in single GPU runs. So if we have like multi GPU process exactly like number of GPU into number of into samples per GPU, then like scaling efficiency will be 1, which is 100%, which is perfect scaling. Doubling GPU doubles throughput. So if we have say example, I have a single node which processes 100 samples per second, and we have 4 GPU which can process 350 sample per second. So this is like 1 and this is like 4. So the scaling efficiency is 350 divided by the linear means it should be 4 into 100, 400. So this will give 0.875. So the scaling efficiency is 87.5. Is it clear? Any doubts? Any doubts? So if no doubts, then we can end today's session. Thank you so much for joining. Okay, so I will end today's session.